Hello guys, and our ODE project is all about AC clock. And our group is composed of Lin Guanheng, Zhan Yihou, Wang Yuchen, and Liu Yuxian. So let's move on. And what is an AC clock? An AC clock is a clock that works only when you attach your clock to AC power supply. And why an AC clock? It seems like AC current is the easiest way for us to realize the clock, since the frequency of AC in Taiwan is usually 60 Hz. So if we attach our circuit to socket, and we could get a 60 Hz sine wave, and the peak-to-peak value is approximately 310 V. So how to use a clock? It's quite simple to use a clock, as I mentioned. Directly attach the clock to the socket. And about the most important part, how does the clock work, and what's the principle hidden behind the clock? And we divided the realization of clock into several parts: voltage transformer, clipper, RC integrator, motor, and some gear. And we decided to build a clock in counter digital clock way, so of course we need some gears here. Voltage transformer is on the basis of Lenz's law, and based on what we've learned in general physics, when current on the left part of the voltage transformer, which called primary coil here, changes, and according to Lenz's law, magnetic field changes accordingly. And let's move on to the right hand side of the voltage transformer, which called secondary coil. When magnetic field changes, change in magnetic field leads to change in current on the output circuit. So we could get an AC power supply on the secondary coil, and the ratio of the number of the coils in primary and secondary coil is proportional to the ratio of the voltage.
Hello everyone, if you want to know how the circuit works, let's have some physical derivation. First, let's draw a RC integrator circuit. To calculate the time in the circuit, we need a conversion in the circuit before it can be used. Our group used resistor and capacitance integrator to convert the output into ramp signal waveform. First, we need to derive the square wave of the circuit using KCL, Kirchhoff current law, to get the following formula. By this derivation, you can get the following relationship. From this, we can see that the output terminal is integration of the input terminal. Next, by theoretical calculations, it can be concluded that the square wave is a ramp wave after integration, so we can use this feature to value the time. We can set a value as long as this value, the output will have a change or move. But we still find out that the output voltage of the above circuit is too small, so we will use an amplifier to amplify the voltage. According to the calculation formula of the amplifier, it can be used to adjust the output magnification. By the simulation's results, the output voltage amplitude of the RC circuit is about 0.6 volts. We probably need a magnification of 10 times. So according to the amplifier formula, V out equals to 1 plus R2 divided by R1 multiply V in. So a circuit with a circuit with R2 divided by R1 of 9 times is needed. After combining the two circuits, we can get the circuit part we need.
We use clipping circuit to control the output voltage by connecting a resistor and a diode in series. The output voltage is the voltage of the diode. We assume that the diode satisfies the constant voltage drop model, which means the voltage drop is 0.7 volts. Then we can see that the output voltage won't be higher than 0.7, even though the input voltage is still increasing. For the second circuit, the two diodes are put in opposite directions. If the input voltage is positive, then the diode of the right-hand side will be cut off. Only the left-hand side will work. As mentioned before, the maximum value of the output voltage will be 0.7 volts. When the input voltage is negative, the diode of the left-hand side will be cut off, and this time the diode of the right-hand side will work. Now the minimum voltage of the output voltage is minus 0.7 volts. And the same principle can also be applied to sine wave. In the graph of the waveform, we can see that between minus 0.7 and 0.7 volt, the magnitude of the output voltage will equal to the input. When the input is higher than 0.7 or lower than minus 0.7 volts, the circuit will clamp the voltage. So we can control the range of the output voltage to stay between minus 0.7 volt and 0.7 volts. In our circuit, the input voltage is an AC voltage source, and the magnitude is 10 volt as we reduced it before, and the frequency is still 60 Hz. And the picture shows the result of our LT-SPICE simulation. As you can see, we successfully clipped off the part which the magnitude of the voltage is above 0.7 volts, and we transformed the sine wave into square wave so that we connect the output voltage to the motor, and the gear of the motor will push the clock to rotate. The reason why we need to convert sine wave to square wave is because if we just use sine wave, then after integrated, it will simply become a cosine wave. But if we use a square wave, then after the integration, we will get a triangle wave. Then we can make use of the triangle wave because we can define a specific threshold value so that the motor will rotate as long as the voltage is higher than that threshold value. And for every 1/60 second, the motor rotates. So in this case, we will be able to make a clock by using gears with different amounts of tooth to let the pointer rotate for every 1 second. And that's how our clock works.
I use basically FreeCAD to design the gears of a clock, and the gears on the slide is a schematic diagram, and I would probably design a real one later. And the clock could do most of the things that a traditional clock could do. For example, the measurement of time.
Now I would like to show the simulation of the clock design. It is implemented using Python. We will run the program to see how it works. First, we see the ideal clock model. It is a simulated clock, where the minute hand is a cyan one, and the second hand is a magenta one. Now we remove the board to see the detailed structure of the model. The axis of the minute hand is embedded in the green internal gear, and that of the second hand is embedded in the red gear. Note that the number of the teeth of the green gear should be 60 times larger than that of the green gear, but seemingly Python is not able to draw the gear with too many teeth. We set the ratio of the number of the teeth to be 10 instead of 60. Now, we talk about the direction of the gears. The red gear, the yellow gears, and the green gears rotates in the same direction, while the orange gears rotate in the reverse direction. The rotation of the magenta axis is driven by the motor, and thus the red gear is driven, and the orange gears are driven. And then the yellow gears, the green gear, and finally the cyan axis embedded in the green gear. Now we are going to introduce about the physical principle of the rotation of the gears. The ratio of the number of the teeth of the red gear, orange gears, yellow gears, and the green gear in our realization would be 1 by 1, 1 by 1 by 60. As the number of the teeth of the gears is proportional to the angular velocity, the angular velocity of the red gear, orange gears, yellow gears, and the green gear in our realization would be 1 by 1 by 1 by 60 as well. Let's take a deeper sight to the graph. The gray cuboid denotes our design that can transmit a pulse per second. It is connected with the motor, which is the white cylinder, and the motor is the source to bring the motivation to the clock system.
The last part is about a further plan, literally something we plan to do in future. As we mentioned, we will build the aforementioned part definitely, and of course link of them with the breadboard. Some of you guys might ponder why there's no amplifier. It is because we haven't decided the realization of it, either by the from the web or build an amplifier ourselves. And if you have any questions about our ODE project, feel free to leave the messages below.